In this discussion, we are going to need a number of quantities frequently. So let's get acquainted with them. We have this model y equal to x beta plus epsilon, and we are going to fit y hat. So y hat equal to this thing. Now this matrix, this thing from x and going all the way up to x prime, that's a matrix which is basically the orthogonal projection operator onto column space of x. We generally call it the hat matrix. Hat because it puts a hat on y. So if you multiply y with h, it becomes y hat. So we call it the hat matrix. The diagonal entries of this hat matrix are going to play an important role in the discussion. We call them hi. It is the ith diagonal entry of h. We are not calling it hii, I just call it hi, and these are commonly called the hat values. Now we are trying to delete one row at a time and see the effect on the various aspects of the fit. Accordingly, we define xi to be the ith row of x. Remember that xi is a row vector. So if x is n by p, it is a 1 by p vector, a row vector, a horizontal one. And if you remove that, whatever remains of x, that n minus 1 by p thing, that I will denote by x, then round bracket I. It is x without that xi. Everything else in its place, you have just deleted the ith case. Now if we do the fit based on only that x round bracket I thing, the resulting fit I will denote by beta hat round bracket I. That's a vector, a p-dimensional vector. This I means which one has been dropped. Similarly, sigma square hat I is sigma square estimated based on all but the ith case. Now the first thing that we are going to discuss in terms of the effect of deleting the ith row will be on the betas. The resulting quantity we will call DFBETA. I have called it DFBETA I, so that subscript I means I have deleted the ith row and I am saying what is the effect on the estimated value of beta. So it is defined in this simple way. You take beta hat, the fit that you obtain from the entire data, then you also fit the same model on the deleted thing and you get beta hat I. You take the difference between them, you call it df beta I. So if there are n cases, then you have df beta 1 to df beta n. Now these quantities, you want to naturally say if this is large, then that point is going to be influential. But as we all know, just to say something is large is not good enough. We have to take into account the variability of this quantity. That is, we should somehow standardize it by dividing it by its some measure of dispersion. So if I divide it by its standard error, in that case we get what is called df beta s. Now the different quantities, remember this is a vector, so its different components will have different amount of variability. So you have to divide it by a different quantity. That is why I have called them df beta s ij. Remember df beta, these are all vectors, p-dimensional vectors, and these are all scalars. Now I have unpacked them in terms of their separate entries because I need different scaling factors for the different entries. And this quantity downstairs is pretty obvious. We already know that sigma squared times x prime x inverse is the variance, is the covariance matrix of beta hat. So what I do is that I take its jjth entry, that is the diagonal entry, which is sigma square times x prime x inverse is jjth entry. I take its square root, so this is sigma. Now unfortunately I do not know sigma, so I have to estimate it. I use the deleted estimate of sigma, and that is natural because when I am removing the ith row, it is basically that I am suspecting that it might be too influential. So keeping that in the model might give me misleading estimates, and that is why when I need a reliable estimator of sigma, I am not using that particular case. So in place of sigma, I am plugging sigma hat I. So this quantity is called df beta Sij. So this is basically a matrix. This is the ijth entry of that. This matrix is of the same size as your X matrix, n rows and p columns.